Corrosion Kinetics example 2. So what this says is that it's given a parameter univalent, meaning that n is equal to 1, right? And we're given all this. It wants us to find the current densities, anodic and then the cathodic, right? When the metal is anodically polarized, right? So this basically here means that overpotential anodic, right? So if overpotential anodic is 0.20, we know that the overpotential cathodic gives a sample reaction, right? It will be negative, this positive, right? It will be negative 0.20. And we know this one will be in millivolts, right? Millivolts. And this as well will be millivolts, right? So they want us to find the current densities, anodic and cathodic, right? So we start with the, so, and it says hence determine the experimentally measured current density, right? But let's see. You see, it actually specified that we should find, it said it's anodic polarized, right? So that's why we get this here to be anodic, and because it's a simple reaction, we said the cathodic will have the same magnitude, right? Okay, so let's see. So let's start with the anodic, right? Okay, same example. So we have anodic, we know the equation already, right? And then we've been given the anodic, right? So the anodic is 0.2 for potential a minute. This anodically polarized, right? Anodically polarized, so 0.2, right? And then we have for that is 0.2 as well, right? And then we have log, and then we have another current density, and we have a Hessian current density, which has been given us 20, right? Remember the unit very important. Here we have milliamperes per meter squared, very important. So that will mean that we can get another current density from this, right? Another current density, another minute, right? So there we have let's see, 0.2 equal to 0.2. We have log is 10. Then we have what we are looking for, the another current density, and then we have the exchange current density, 20 milliamperes, right? So that gives us the another current density 200, but remember in milliamperes, so that will be milliamperes per meter squared, right? Just as the exchange current density, right? So we are done for the anodic half, right? So cathodic, same procedure, right? So let's see. So the potential was not given, but we know that to be the same magnitude, right? But let's look at this. We said we have to maintain one of them because of how that particular one is, right? So if from what has been given in the equation, the cathodic is positive, then we maintain it as negative is the appropriate way of doing it, right? So that will mean that we have the potential as minus 0.2, right? And then the B is BC is 0.2 Tafel constant cathodic, right? And then we have log, and then we have IC exchange current density 20, right? Let's see. The only difference is here is minus 2, minus 0.2. Yes, it's the same. So let's see. Okay. So that gives us the cathodic current density of 2 milliamperes, right, per meters squared, right? So we are to, so it says we should find the experimentally measured current density, right, which is basically the net current density, right? So that's the net or measured, right? It will be the same as anodic minus cathodic, right? And then we have 200, and then we have 2, right? So that gives us 198 milliamperes per meter squared, right? So that's it for this particular example.